Hello everyone, and welcome back to another GIS lecture video. And in this lecture video, I want to continue our discussion talking about feature patterns, right? Whether or not the locations of a particular data set exhibit some sort of either clustering or dispersion. And what we're going to talk about in specific in this video is this idea of something called nearest neighbor. Right, nearest neighbor. And so broadly what we're doing is we're taking this idea of the average distance between any point and its nearest neighbor, and we're going to compare that to what we would expect the average distance between points to be. Compare those two and then determine whether or not our value is higher or lower than that average and whether or not that difference is significant. So to sort of repeat that, what we're going to do is we're going to calculate the average distance between every point and its nearest neighbor. We're going to calculate the average distance between every point and its nearest neighbor. Okay? So in order to do that, we have to come up with an equation. Well, we're taking the average, so we're going to be dividing something by n, right? That's what it means to take an average. Well, what are we going to be dividing? Well, we're going to be dividing the distance between every point and its nearest neighbor. So we're going to have a distance, which we're going to call I, and we're going to sum that distance between I and n, right? And so in specific, right, this distance is going to be the distance between I and its nearest neighbor. The distance between I and its nearest neighbor. Right, this n we've already seen before. This is the number of points. Right, and we're going to call this distance, this average nearest neighbor distance, we're going to call this d for distance. Let me clean that up a little bit. So we're going to call this d for distance, with an average sign indicating that it's an average distance, and then we put a subscript O here because this O is going to represent our observed. So this is the observed average distance. Okay. Average nearest distance, sorry. This is the observed average nearest distance. Okay? And so I think it's helpful to go through a worked example of how this will work. So in order to get this, we have to calculate the distance from one point to every other point, and then find the smallest value or the smallest distance. Okay? And so what I want to do is I want to go through this particular worked example here. So we have 15 points, and you can see that they're plotted over here on this map here. And so looking at this, you might expect, well, hey, maybe this data is actually clustered, right? Maybe there is some clustering, or maybe you think it's dispersed. Well, we don't really know for sure. That's why we're doing the analysis. So what we're going to do is we're going to calculate the distance from one point to every other point, and then from another point to every other point. And what we end up with, if we switch over to Excel here, is what's called a distance matrix. Right, so these are the data points over here. This thing right here, this is our distance matrix. So what you have is you have the points represented as both the rows, right, the rows, as well as the columns. And the number in this matrix represents the distance between those points. So for example, this distance right here is the distance between point 1 and point 2. Right? If we pick another one at random right here, for example, right, this is the distance between point 10 and point 9. Okay? So all this is just the distance from every point to every other point. So in order for us to calculate a good average nearest neighbor distance, what we need to do is find the nearest neighbor. So in order to do that, all we have to do is look at a particular column or a particular row. I prefer to work in columns, is to look at a particular column and find the shortest distance, right? Because this column, for example, represents the distance from point 1 to every other point in the data set. If we find the distance that is smallest, then we've found the nearest neighbor, because again, right, the nearest neighbor is going to have the shortest distance. So this row down here, all I've done is I've just written a quick Excel code to just search each row and find the smallest value. That's not 0, smallest non-zero value. In this case, there's no points on top of each other, so I was able to do that. But as you can see here, right, the minimum value here is 1. So the nearest neighbor for point 1 is going to be point 11, and that distance is going to be 1. Okay? And then we just repeat that process for all the other points, right? So again, for example, here, right, the nearest neighbor distance is 2.24, and you can see that that corresponds to point 8's nearest neighbor being point 1. Okay? So hopefully this idea of the distance matrix makes sense, and the fact that all we're doing is looking at each column and finding the shortest distance. Okay? So let's go ahead and clean that up a little bit. So what I've done here is I've taken, these are just the nearest neighbor distances for all of the points. So this would be point 1, point 2, point 3, point 4, etc. This is just the same numbers we found before. I just rotated them 90 degrees because I prefer to work in columns. Right? And so all we do is we take the average of the nearest of these nearest neighbors. So we get an average of 4.40. Okay? So let's hop back over to our thing here. And so we now know that for this particular example, right, our nearest neighbor distance, our D, actually let's do this in blue. Right, for this particular example, we know that our D observed average is going to be 4.40. All right, so we've calculated the average distance between every point and its nearest neighbor. So now what do we do? Well, we need to compare that to something, right? Because that's the whole point in doing these tests, is to compare what we have to something that we would expect. Well, in this case, what we're going to compare that to is the expected average distance given a random distribution. Right, expected average distance given a random distribution. So what would the average distance of a random distribution look like? Well, fortunately for us, we don't need a whole lot of information. All we need to know to figure out what we need for our average distance is the area that the study is covering, and we always denote that, as always, with a big A. So we need to know the area the study is covering. We need to know the number of points, right? And this right here would give you the average number of points per unit area. We'll take the square root of that. And then this part is just another one of those times where we just have a constant. And this constant in this case is going to be 0.5. Okay? and we're going to set this distance. We're going to call this the distance, so it's going to have a d. Average, because it's the average distance of what? Of our expected data, right? So this average d sub e is going to be the average expected nearest distance. Right, so this is going to be the expected average nearest distance. Right, expected average nearest distance. At this 0.5, this is just a constant. So anytime we do these calculations, it's always going to be 0.5. This n, again, is number of points. And this a, this is the area, again, of the study area. Okay. So let's go ahead and we can do this calculation without having to go to Excel. To get the average number of points, or the average nearest distance expected, we need the number of points. Let's go ahead and plug this into our equates. Let's scroll down just a little bit and give ourselves a little bit of space here. Right, for our particular example, this DE, this average DE, is going to be equal to 0.5 divided by the number of points we said was 15. Well, what's the area of our study area? Well, in this particular example, we go from 0 to 30 in both directions. So we know that this distance is 30. We go from 0 to 30 in this direction, so this distance is also 30. So our area is going to be equal to 30 along one side times 30 along the other, or 900 units. In this case, we don't have a spatial reference because we're dealing with just numbers and a graph. But our area is going to be 900. Right? And so if we do those calculations, what you end up getting is 3.87. Right, so our DE average, or our average expected distance, is 3.87. Okay, so how do we interpret this? Let's go ahead and give ourselves a little bit of room. Let's recopy down our D0 naught. We had as 4.40, and our DE naught is going to be 3.87. Okay, so how do we interpret this? Okay, let's think for just a second about what this D average, this D sub 0 or D sub O sub average is actually indicating. All right, it's the average minimum distance. So the smaller this average minimum distance is, the closer together the points are going to be. All right, so if you think about that for a second, right, the smaller the average minimum distance, the closer together the points are going to be, which means this could be an indication, right, that there's clustering, because the smaller the minimum distance, right, the more likely points are closer together. Points that are closer together are likely to indicate clustering. Now again, this is relative to the size of the study area, but that's where this DE comes in, because this is incorporating that size of that study area. Right? So under random circumstances, right, this is what you would expect to see. This is what you actually got. If you compare these two together, right, if you take the O that you have, right, if you take D sub O and you subtract off, right, the expected, well, what do you get? Well, if D sub O is larger than D sub E, you're going to get a positive difference. Right, a positive difference, which means that this number was larger than this number. And again, right, we said that if DO was really small, that might indicate clustering. Well, if DO is really big, that might indicate dispersion, again, based on the size of the study area. Well, if we take the difference here, we've taken into account the size of that study area. So if this is much larger than this, you get a positive difference. That positive difference might indicate dispersion. Right? This might indicate that the data is dispersed. Well, what happens if you get a negative difference? Right? Again, that would mean that this distance was smaller than this one, which means the points were close together because the distance was small. More importantly, they were closer together than you would expect by chance. So if it's closer together than you would expect by chance, i.e., this number is negative, that might be an indication that you have clustering. Right? That could be an indication that you have clustering. And then if it's 0 or close to 0, right? If there's 0 difference, then that could be an indication that your data is actually random. Right? So hopefully that makes sense. This idea that you have your average nearest neighbor distance, you're comparing it to what you would expect given random. The farther apart these values are, the more likely you are to have some sort of pattern. If you have a high positive difference, that could be an indication that the points are farther apart than random, which would be dispersion. If you have a large absolute value negative difference, right, that would mean your points are a lot more close together than you would expect under the random distribution. And that could be an indication of clustering. And if you have no difference or very little difference in terms of absolute value, that is an indication that your data is more than likely randomly distributed. Okay? So hopefully this made sense, how we went from this idea of a set of points, calculating the distance between every point and every other point, using that distance matrix to get the minimum distance, so the distance to the nearest neighbor, taking the average of that to get our averaged nearest neighbor distance, calculating the expected average nearest neighbor distance by incorporating the number of points, the size of the area, and this constant, and then simply comparing them to see what the difference was. So hopefully this all made sense. In the next video, we're going to briefly talk about how we can take this difference and then determine if it's statistically significant or not. So if you have any questions, as always, please reach out. Thank you.